All right, in this video, we're going to start talking about Note 17 from Calc AB, which is all about something called the second fundamental theorem of calculus. To deal with the second fundamental theorem, we do need to know something about a weird type of function. It's a function that has a definite integral in it, and that is going to be called an accumulation function. So an accumulation function is literally what I just said. It's a function that has a definite integral in it. So sometimes, like the one that you can kind of see above it right here, there's really no reason for this to be an accumulation function because we can find an antiderivative, we can use the fundamental theorem. But sometimes we won't be able to figure out an antiderivative, and then we're going to need to deal with it somehow. Second fundamental theorem is going to tell us a lot of how to deal with that. So let's see if we can get rolling on this. So an accumulation function with a definite integral in it somewhere. They're pretty neat. They might actually be my favorite types of functions because it feels like you can do anything with them. So let's see if we can fill this in. So given the function, use a calculator to fill in the table. It's actually faster to do these by hand, which it actually says here. So the reason that it's faster to do these by hand is if we graph the integrand, right? So I'm going to graph 2t. So 2t maybe is like this. I don't know, right? 2t. So you can kind of see that, for example, the integral from 0 to 0 of anything is just 0. So we can fill in 0 right away. Now, the integral from 0 to 1 of this thing, so if I put like a little 1 here, the integral from 0 to 1 is actually just this area. But that's a triangle, right? So this is 2 because the function is 2t. So if t is equal to 1, then 2 of that is 2. So half of, so it would be a rectangle that has an area of 2. So half of that is 1. When I get to 2, this will be 4, right? And then the region that I want is this whole thing, right? Because I'm going all the way to 0. Well, that's just half of, so that rectangle would have an area of 8. Half of that would be 4. If I go to 3, we got to go up to 6. So it'll be this. And then, so this is 6 by 3 is 18. And then divide that by 2, we get 9. Are you seeing something here? 0, 1, 4, 9. So this one, when we find it, will just be 1/2. The base is 4. And then the height is going to be 2 times 4 is 8. So that's going to be 16. Here we get 1/2, the base is 5, the height is 10. So that's going to be 5 times 5, so 25. Perfect squares. Look at that. You don't really need a calculator. You could use a calculator, but you don't need a calculator. Now, if you think about the other direction, right? So we're going to have to use a property of our definite integrals here. So the first thing, I'm going to redraw it so that we can think about this. So, well, I'm going to redraw something. So here's sort of our line. So if I go to -1, so -1, double that, you get -2. So the integral, so the function is telling me to find the integral from 0 to -1 of 2t dt. But when using the fundamental theorem, the lower bound should be smaller than the upper bound. So actually, I should flip this and make it the negative of the integral from -1 to 0 of, well, 2t dt. So what's happening there? Well, the integral from -1 to 0 would be half of a rectangle that has an area of -2. So it'd be -1, but I want the opposite of that. So I'm going to get +1. What if I went to 2? Would it be any different from what happened before? We're down at -4. So I want half of a rectangle that has a base of 2 and a height of -4. So half of -8 is -4, but I want the opposite because I still have to flip it. So for all of these, like here, I want the negative of the integral from -2 to 0 of 2t dt. And then here I want the negative of the integral from -3 to 0 of 2t dt, because the lower bound should always be smaller. So what's going to actually happen is that we're just going to do this, and you can work these out if you want, but it's going to happen. So we just get the perfect squares. Should we be surprised by this? Probably not. Let's see. So if I graph f of x, so I'm plotting the points from f of x, so 0, 0. This scale is rough. So 1, so I'm going to skip that one for now. 2 gave me 4, 3 gave me 9. The scale, man. 4 gave me 16, that's a good one. 5 gave me 25, which is kind of like up there. And then we got to duplicate it over here. So like here maybe, and then here I think definitely, and then a little bit over this. So let me just fill this in. Try to do it in one shot, but it's not going to work. Here. Okay. And then this way, maybe I'll try going back this way, which I never really do. I usually start at what appears to be the vertex and go, but it's not terrible. All right, what does this look like? Well, this to me looks like f of x is actually just x squared. Is f of x x squared? So f of x is defined to be this. So what I could do is I actually could say that f of x is the integral from 0 to x of 2t dt. So fundamental theorem tells me that would be t squared from 0 to x, which would be x squared minus 0. So f of x is in fact x squared. We were able to figure out values though without finding f of x. That's the big idea here. That's one of the big ideas. That's like half of the big idea. You can find values of an accumulation function. An accumulation function, a function that has a definite integral in it. You can find values of an accumulation function without actually finding the antiderivative. You don't actually need to use the fundamental theorem because what you can do is you can use the fundamental theorem all the time, right? But just for definite integrals. So all we need to do is find areas, bounded regions, and we'll know values of the function. So that's really interesting because it means that the integrand in your accumulation function could be like anything, right? Cosine of x to the third doesn't actually have a simple antiderivative that we can find. We could still put in an accumulation function. That's going to be the big idea. So let's see what we can do here. So I'm going to apply the fundamental theorem to each of the given functions to eliminate the integral. So what's weird about this, as we know it, the fundamental theorem, you should be going from a constant to a constant, like a to b, and a and b are both real numbers. This, we have a function. We're going to go for it. It's going to be okay because when I give you a value of x, for example, in this first one, it's going to create sine of whatever that value is, and now it works. So we're just doing it in general. So here, this would be 3t from 1 to sine of x. So t is called a dummy variable, which sounds mean, but it's not. And what we're doing is we have to use something other than x, because if I give you an x value, you should change every x that you see to that x value, and we don't want to change it if it's inside the integrand, right? So we need to use a dummy variable. It could be anything that's not in the problem. So we had f of x. So every variable other than x and f were available to us. Often you'll see t, often you'll see u. Those are probably the two most common. So here I've gotten 3 sine of x minus 3. That's good. Here, okay, so first I'm going to integrate the integrand. So what gives me cosine? Well, sine of t. And then what gives me 1 is t. I got to go from 0 to 2x. So that's going to give me, so let's say this is f of x. It's going to be sine of 2x plus 2x. And then if I substitute 0, I get the sine of 0, which is 0. And then when you make t equals 0, you get 0. So this is actually our f of x. So let me highlight the ones that are done. So this is done. And then this is done. Okay. And then we're going to keep going. So there's a note below this one. So f of t is the integral from 1 to t squared of natural log of x dx. So notice I'm using x because the variable in question is t, right? Here's t. So that's why we're using x and dx, because we need a dummy variable, and t was already used, so now I can use x as my dummy variable. Dummy variable is just in the place of the variable. Like the function is actually a function of t. we need that dummy variable so that, like, if I tell you that t is equal to 3, if you had natural log of t on the inside there, then does that t become 3 or does it stay t? It's confusing, so we use the dummy variable for that. So this has a hint to it because you may not know this yet. The integral of natural log of x is x natural log of x minus x. I have a friend who teaches a lot of physics, like in college, and he says it would be extremely helpful if everyone would memorize that. So you could memorize it for now. Later in the year, we'll find out why it's x ln of x minus x, but take the derivative of x ln of x minus x and see what you get. You're going to get natural log of x. So here, f of t is going to be, so first we get x ln of x minus x, and we're going to go from 1 to t squared. So f of t is going to be, first we plug in t squared. So t squared, natural log of t squared, minus t squared, minus quantity 1 times the natural log of 1, and then minus 1. Okay, the natural log of 1 is 0, so that's going to be gone. And so we're actually just going to get that f of t is t squared, natural log of t squared, minus t squared, and then plus 1. And that, I think, is our final answer on that one. Okay, and then one more. So here we have f of r. So r is actually the independent variable, which is why we're using t as our dummy variable, right? We can't use r because if I tell you that r is 0, what happens to that 2 times r plus 1? Does it just become 1 because r is 0? Does it not? It's confusing. To avoid the confusion, we use a dummy variable inside the integrand. Always on these. Always do it. All right, so let's see. F of r. So we'll integrate and get 2t plus t. Sorry, t squared plus t. And then t goes from 2 to r squared. So f of r is going to be, all right, so we plug in r squared and we get r to the 4th plus r squared minus the quantity 4 plus 2. Then we clean this up and we say that f of r is r to the 4th plus r squared minus 6. Okay, that, I believe, is our answer to that. So we just use a fundamental theorem on these accumulation functions. It's really unusual to be able to do that. The process we just went through is very strange. Usually you would have something as your integrand that you actually can't find the antiderivative of. That's what makes these so special. We can still deal with them, but like we would need a lot of technology to actually find the value of like f of 5. But you could do it with technology. So the really odd thing about these that's different is that for all of them, the upper bound was a function. Not a constant. So this is different, right? The answer to a definite integral is going to be a number. The answer, if you could evaluate an accumulation function and get rid of the integral somehow, the answer is actually a function. So these had functions as their answers instead of numbers. So had functions as their answers, not numbers. So usually when you use the fundamental theorem, you get a number, right? A definite integral is just a weird way of writing a number. In this case, because these are accumulation functions, the definite integral, when we were able to evaluate it, turned out to be a function. It was not a fixed number, but it would be a number. If you knew what the independent variable should be, you would sub it in, get a number. So it's like a lot going on. So I'm going to come back in the next video and do even more with these. So like, where are we going with this? We don't really know yet, but we'll know soon. So I will see you in the next video.